You're watching Electrical Engineering Lectures channel. For more videos, please do like, subscribe, and hit the bell icon for the latest notifications.
Hello everyone. In this lecture of digital signal processing, we will be discussing the concept of bandpass sampling. So actually there are two kinds of sampling. The first one is called Nyquist sampling. And the second one is called bandpass sampling. It depends on the types of signals. If you are going to sample a baseband signal, you usually go for Nyquist sampling. And for performing Nyquist sampling, you need to fulfill the Nyquist criteria. Right? And whenever you are going to sample passband signals, then you will go for bandpass sampling, and the criteria is bandpass sampling theorem, which we will discuss in this lecture. The reason to move towards bandpass sampling is that whenever you are going to sample passband signals by using Nyquist criteria, it will require much higher sampling frequencies than you can afford. For example, if a passband signal is centered around 1 gigahertz and it has a bandwidth of, let's say, 5 megahertz, then you need to sample that passband signal. Please, you have to sample it at a sampling rate of more than 2 gigahertz. But if you use bandpass sampling theorem, then you can still sample the passband signal at very lower sampling rates by avoiding the aliasing. So what is the main concept behind bandpass sampling? First of all, we will discuss some specific examples, and then we will move towards the generalized bandpass sampling theorem. Let's say we have a bandpass signal shown in this diagram, which has higher frequency equal to 3 times B, where B is the bandwidth of the signal, FL is the lower frequency, FH is the higher frequency, and FH is equal to 3 times the bandwidth, right? And FS, let's say we sample this particular passband signal at Fs is equal to 2B. Now, as per Nyquist criteria, we have to sample it at least greater than 6 times B. But here we are saying that we are not following Nyquist criteria and we sample it at a sampling rate of 2 times B. So if we sample at 2 times B, you see we will definitely get multiple copies, because whenever you perform sampling, you will get multiple copies at integral multiples of the sampling frequency. So for example, this is the first copy that you will obtain at plus minus Fs. This is the second copy that you will obtain at plus minus 2Fs. This is at plus minus 3Fs, and so on. And if you add them all point by point, then you will get this particular result. And in this result, you can see that the actual spectrum of that passband signal is recovered in the form of a low pass equivalent signal. These two copies, the right side copy and the left side copy, both are now located at the baseband. So in this way, without following the Nyquist criteria, we sample the passband signal at a lower sampling rate. Still, we are able to avoid aliasing. So now we can formulate two different cases such that the higher frequency FH is equal to K times B, where K is an integer or a non-integer. And in the first case, we can further have two cases. If K is an integer, it can be odd and it can be even. So it means we will first find out the bandwidth of the passband signal and then the higher frequency of that passband signal, and we see that what is the situation of this number K. If that is an integer, we are into the first case. If it is a non-integer, then we are into the second case. And being an integer, it can be odd or even. So if that K is an odd integer, what will happen? You see, this is an example where FH is now 5 times B. So K is equal to 5 in this particular case, 5 times the bandwidth. Again, we can choose Fs is equal to 2B, 2 times the maximum bandwidth. We select this criteria for the sampling, and if we sample at this sampling rate, then by using the same technique just discussed earlier, you can see that the actual copies of the passband signal are now located at the baseband in the form of a low pass equivalent. And if K is an even integer, like for this example, if K is equal to 6, then FH is equal to, here FH is equal to 6 times B. So for this particular case, now if you again sample fs at fs is equal to 2b, this spectrum, then you will see by following the same procedure, you will see that now you will get the same two copies of the passband signal at baseband, but the difference is that these two copies are flipped. The right-sided copy has gone to the left and the left-sided copy has gone to the right, but that flipping is not a big problem, because in any case we are going to formulate a low-pass equivalent model, and for low-pass equivalent it doesn't matter that either the copy is located on the left or it is located on the right. Simply we need to low-pass filter it, and then we can adjust the content of the right-sided and left-sided copies. So it means that when k is an integer, either it is even or it is odd, it is not a problem. We do not encounter any problem of aliasing if we sample at fs is equal to 2b. But remember, this is not always true that k is an integer. In most of the cases, k is not an integer. Therefore, this approach cannot be followed in general. We need to formulate a generalized mechanism to find out the conditions that at which sampling rate we need to sample the passband signal so as to avoid the aliasing, right? So for this, we consider a generic model and try to find out the criteria for sampling the passband signals. And to have that criteria, let's suppose there is a passband signal and to have this criteria, let's say there is a passband signal whose spectrum is like this, with the bandwidth of capital B. This point is FL, this point is FH, and similarly same thing on the right side. And just to see the difference, we can consider the opposite copies. It is minus FH and it is minus FL, right? Now let us consider any arbitrary integral multiple of the sampling frequency. Let's say we talk about the integral multiple of the sampling frequency in the form of k minus 1 times fs. So at this sampling frequency, the right-sided copy, which is this one, the right-sided copy, let's assume that it comes somewhere over here. And the right-sided copy definitely is on the right, which I am not going to plot. So this is your left-sided copy corresponding to k minus fs, right? Similarly, let's consider another frequency which is kfs, the next to k minus 1. So for this kfs, again the left-sided copy, let's assume that it comes over here. And again, I'm not plotting the right-sided copy, it will be somewhere on the right. So these are the two copies. This copy corresponding to k minus 1 fs, and this copy is corresponding to k times fs. Now we have to formulate some labeling in order to find out the condition. First of all, let us see that the range from this point to this point, what is this range? Because from this point, from origin to FL, it is FL, and same on the other side. So you can say that it is 2 times FL, right? This is the first point. And secondly, what about FH? For FH, you should observe that this particular point and this particular point, if you see this range, it comes out to be 2FH. Okay. Now you see, this point is k minus 1 fs. So the distance from here to here, this is k minus 1 fs, right? But if I subtract this distance, this range, which is what? This is basically equal to FL, because it is corresponding to this much, because this copy is actually shifted at the at k minus times fs. So it means this range is equal to FL, right? So if I take this FL over here at this point and I mark the range starting from here to here, so you see, what should be this range? This must be equal to fs into k minus 1, because from this point to this point, it is k minus 1 fs plus fl, right? And this distance is also fl, and this distance is k minus 1 into fs. So I have just swapped the two variables. I have taken fl towards the left and fk minus 1 fs towards the right. So in this formation, it is k minus 1 fs. Similarly, by using the same approach, you can also label here k times fs. So if I start from fh and I go until the lower end of this point, so what about this range? This range will be k times fs by using the same approach as I have already told you about k minus 1 fs, right? So these are some variables that need to be labeled. Now, if I want to avoid aliasing, it means I will want that this point and this point, they must be distant from each other. They must be distant from each other. It means the first condition that I have is that k minus 1 fs must be less than or equal to 2 times fl, because the first red dot is corresponding to k minus 1 fs and the second red dot is corresponding to 2 times fl. Okay, so now what about the second condition? Now I also want to avoid aliasing by keeping this point less than the second red dot. Now here the first red dot is what? It is 2 times fh, and the second red dot is kfs, so it must be less than kfs, right? So I have got these two inequalities. Now let us try to solve these two inequalities and try to find out some condition, and by using the fact, of course, that b is equal to fh minus fl, so that fl is equal to fh minus b. fl is equal to fh minus b. Okay, so here it becomes k minus 1 fs less than or equal to 2 times fh minus b, and from this inequality we can write 1 over fs is less than or equal to k over 2 times fh, right? Now if you just multiply these two, if you multiply these two inequalities, the resultant will be k, because the direction of inequality is the same, so we can directly multiply the right side with right side, and left side becomes 2k fh minus b divided by 2 times fh. Now if you solve this inequality, fs is cancelled out from here, and on the right side it becomes 2k fh divided by 2fh minus 2k b divided by 2fh. So here fh is cancelled out, 2 is cancelled out, here 2 is cancelled out, and here we are left with k minus 1. Further solve it to get here k as common into 1 minus b over fh. If you solve this inequality for k, you will end up with this inequality, k less than or equal to fh over b, right? So less than or equal to means if we want to have so k less than or equal to fh over b means if we want to have an integer value of k, then what we will do, we will just floor this result, so it will be equal to fh over b, or we can also say, now if we want to find the maximum value of k, that will become, of course, by flooring the result, so it will be equal to fh over b floor. So that is basically the maximum value of k that you can use, right? So now we see what is happening over here. So we have actually got two conditions. The first condition is this one, which is k max less than or equal to fh over b, and the second condition, which is necessary to select the sampling rate, is this one, that fs is greater than or equal to 2fh over k, and fs is less than or equal to 2fh minus b over k minus 1. This condition can also be found out by using these two inequalities. So you see, if we are here, and you can say from this inequality, you can say that fs must be greater than or equal to 2fh over k. So this is the first one. This is the first equation. And from this inequality, if I take it over here, you can find out fs less than or equal to 2 times fh minus b divided by k minus 1. So by using these two inequalities, rather by joining these two inequalities, you can end up with the same inequality that we have shown in the slide. This is right. So what does it mean? It means that whenever you are going to perform bandpass sampling, and in order to avoid aliasing, you have to select two variables. The first one is k and the second one is fs, right? And if you plot all these inequalities and formulate a region so that you can directly find out the sampling frequency, that will avoid aliasing, right? So this results in a very famous plot that is available whenever we talk about bandpass sampling. And this plot has two axes. On the x-axis we plot fh over b, and on the y-axis we plot fs over b. It has got multiple straight lines and two kinds of regions. The gray regions are called forbidden regions. It means they are the regions where aliasing occurs, and the white regions are aliasing free regions. So whenever you are going to select sampling rate, you need to either use the inequalities, these two yellow indicated inequalities, or if you have this graph in hand, then it is recommended that instead of using inequalities, you straight away go to this plot and directly find out the sampling frequency. Now, how to find out the sampling frequency by using this plot, which results in aliasing free bandpass sampling? The procedure is very simple. You first of all find out fh. You first of all find out the value of fh and b, and you find the ratio. For example, their ratio comes out to be 6.5 in some particular case. So at 6.5, you will draw a vertical line as shown in as a dotted red line over here. And then for a specific value of k, you will draw a horizontal line. Now what must be the value of k? Because the second condition was that k must be less than fh over b, and fh over b is 6.5. So you can select any value less than 6.5, but at most you can select k is equal to 6. Now if you select k is equal to 6, what will happen? Like here k is equal to 3, this is 4, this is 5, and this is 6. So if you select this region, it is very dangerous to operate, because just as a result of a small error, you can just fall into the category of forbidden region. So you will try to avoid these regions. Instead, you will go to lower values of k. So you will prefer to use k is equal to 4 or k is equal to 3. And for example, if we operate at k is equal to 3, it is a normal practice and it is recommended that you select the middle point over here. So you select the middle point and then draw a horizontal line and see where it is intersecting with the y-axis. For example, it is intersecting at 4.7. So it means fs over b is equal to 4.7. And because you have the value of b, so you simply multiply it with 4.7 to result to get the final sampling rate at which you need to sample in order to avoid the aliasing. You see, the selection of k is in your hand and you have to avoid aliasing. So you will prefer go into wider regions and avoid narrow regions to avoid aliasing. So what is the advantage of bandpass sampling? The biggest advantage is that you can sample your signal at a very lower sampling rate in order to avoid aliasing. You can skip the Nyquist sampling. And another advantage comes specifically in case of communication systems, where usually your received signal is most of the time a passband signal, and you have to pass it through a coherent detection to convert it into passband, and then you have to apply a low pass filter, like as shown in this diagram. If x of t is a passband signal, you multiply it with a cos of frequency fc to convert it into baseband, and then low pass filter. And after low pass filter, you have to sample it by using Nyquist criteria, because after conversion to baseband signal, you can always go for Nyquist sampling. But this bandpass sampling ADC, it is basically performing both the operations. That number one, it is basically performing the down conversion, because you already saw that the copies, they automatically convert towards the low pass equivalent, and they are automatically converted to baseband. So that down conversion process is automatically achieved by using the process of bandpass sampling, and at the same time sampling is done, so it is working as an ADC. So you see, bandpass sampling ADC can replace the coherent detection followed by low pass filter and followed by Nyquist sampling. All these three blocks will be replaced by a single bandpass sampling ADC. So that is the advantage of bandpass sampling ADC, because it reduces the parts count. So that's all for bandpass sampling. Thank you very much for watching.
You're watching Electrical Engineering Lectures channel. For more videos, please do like, subscribe, and hit the bell icon for the latest notifications.